Greetings and welcome to Chapter 8, Confidence Intervals. Lesson 8.1, a single population mean using normal distribution. Get to know the new terminology for this lesson. Click on each of the words, learn its definition and meaning. When you are ready, click Continue. We're really starting to get into the meat of this class, which is inferential statistics. We're going to use sample data to make some generalizations about unknown population. One of the key things that we're going to be focusing on are point estimate. A point estimate is just a value that is going to represent the population parameter. For example, we use the sample mean x bar as a good point estimate for the population mean. Now, unless your sample is indeed the population, generally the sample mean won't equal the population mean. We've already discussed this. The sample standard deviation is going to be the point estimate for the population standard deviation. We've already kind of done this in the past. We're just putting a name to it, calling it a point estimate. Another type of point estimate for a population parameter is an interval estimate. We're mostly going to focus on confidence intervals, and I'll explain what that means to be confident interval. But instead of just one value, we're going to provide a range of reasonable values that we feel that parameter falls within. So for example, we run some tests and I can say that I'm pretty confident that the population mean is somewhere between 10 and 15. I don't know exactly what the population mean is, but I'm going to say it's between 10 and 15. So it's the idea of, instead of just one value, I didn't say that I'm guessing that the population mean is 12. Instead, I'm giving a range of reasonable values where we figure the population parameter falls between. Let's say we have a scenario where we're looking at the number of songs downloaded from iTunes per month. Here's a typical wording of a question. Suppose we don't know the population mean. That's what we're trying to build an interval around, is us not knowing what the population mean is. But we do know the population standard deviation, and we'll say it's 1 for this problem. We also know our sample size is 100. Now, we run the data. We can calculate our sample mean. We'll say it's 2. And we select a confidence level. Our confidence level is going to determine the size of our interval. The bigger our confidence level, the wider the interval must be. So let's say our confidence interval for this round is 95. Now, I will say our book uses some different notation as other things out there on the web. C is used for confidence level. Our book uses CL, so pretty much besides this page, I'm going to use CL for confidence level, just so it sticks with our book notation. But C is used and some other notation is used, and I'll explain that later on. We could say, after we run our tests, that we are 95% confident that the unknown population mean of number of songs downloaded from this iTunes thing per month is between 1.8 and 2.2. The 95% confidence interval would be the 1.8 to 2.2. That's the confidence interval. How we interpret it is we say we are 95% confident that the unknown mean is between those two values. So it's not going to only be the calculation portion of the interval, it's also understanding the interpretation of that interval. The 95% confidence interval does imply two possibilities. Either the interval 1.8 to 2.2 contains the actual true mean, or the sample produced an X bar that is not within 2 units of the true mean. The second possibility happens for only 5% of the samples. Here's what it means. 95% of the time, the mean will fall between those two values. The second possibility is that for only 5% of the confidence intervals that we could have created from samples, 5% will not contain the true population mean. So it's totally possible to get a confidence interval and the mean not actually be in there. 95% of the time it will be in there, but that still leaves 5% that it won't be in there. I want to show you in action what confidence intervals really are. We have a normal population distribution. That's this grayish line. We have a sample distribution, which is also normal. It's this red line. And our mean is right here at this green line. I'm going to just start off with a confidence level of 90 and our sample size, let's say our sample size is 50. That's kind of a nice sample size, 50. And out of this population, I'm going to go in and let's just call these people. I'm going to grab 50 people. I'm going to get the data from my people, and I'm going to take the average, our X bar, the sample mean. Using the sample mean, I'm going to construct a confidence interval. So I'm going to take one sample of 50. Here are all my little 50 points out of the population. I calculate the samples average, their mean, and it's this little black dot. You'll notice that the black dot is close to the green line, which is the population mean, but it's not exactly on it. When we construct the interval, it's this black line. Now, what's really important here is not where the black dot is. It's where the black line is. And if that black line crosses the green line, it means our confidence interval includes the value of the population mean. That's exactly what we wanted. We wanted to build a confidence interval that includes the population mean. Now, cool. We did the experiment once, and our sample confidence interval did include the population mean. The more times that we run this experiment, so let me run it one more time. Oh, you'll see I grabbed a sample out of my population. Here's my sample average. I built a confidence interval around it, and you see it's marked in red because it does not cross the green line. So out of the 2 times that I ran the experiment, I was only successful once in quote-unquote finding the population mean, or I should say that my confidence interval included the population mean. Now, the more times that I do this experiment, let me do it a 3rd time, you'll see, okay, this sample that I randomly selected out of the population, and I built a confidence interval using its data, it does include the population mean. Now, instead of trying to run this each time one by one, so let's see, out of the 10 times I ran this experiment, 9 times out of 10, my confidence interval did include the population mean. So 1 time I ran the experiment, it did not include it. But 9 times it did. That's really what it comes down to, confidence level. 90% of the time, if I run this experiment, my confidence interval will include the population parameter, and in this case, it's a mean. I can run this experiment, let's say 100 more times. I'm going to go ahead and do it at 25 at a time, and you'll see my total increase by 25. So out of 35 times, the confidence interval did include the population mean 32 times. Out of 60 times, out of 60 confidence intervals drawn from the population, 55
of the confidence intervals included the population mean. You run it a few more times. 185 times we ran the experiment, and 170 of those confidence intervals that we built did include the population mean. And therefore, I have about a success rate of 92%, which is very, very close to the 90 that we selected. 90 is the theoretical, 92 is the actual out of running experiments, and it's what I would say close enough. Now, you might be wondering, does it matter what my sample size was? So I'm going to change my sample size to 75. I'm going to clear out my experiment, and I'm going to run this experiment with a confidence level of 90, our sample size of n, and I'm going to go ahead and run this about, let's say, 300 times. So I'm just going to go ahead. Here we go. We ran it 300 times, and out of our confidence intervals that we built, 265 of them did include the population parameter of the mean. That's about an 88% success rate. Now remember, I said we might not hit exactly 90%, but that's pretty close. I could run it a couple more times, and we're getting closer and closer to 90% of the time we will include our population mean. There we go. So the more the times that we run it, it will tamp out at 90%. So 90% of the time, our confidence interval that we build will include the population mean. That was changing the sample size. Now let me change the confidence level. Round it up to 95% is a very popular confidence level. I'm going to go ahead and leave it at 75 for our sample size. And I'm going to run this experiment again a couple hundred times. And just watch the percent of success rate of, it means I ran it 25 times, and 24 of the time, those confidence intervals that I built included the actual population mean. Let's run it a couple more times. All right. After 300 times running the experiment, drawing one sample, building a confidence interval, running again, building a confidence interval, out of those 300 confidence intervals, 280 did include the population mean. So we had about a success rate of 93%. I'm going to change my n size to about 40 and run this experiment again. So very quickly, let's draw 300 samples of size 40, and we actually did pretty good here. Out of the 300 that we drew, 295 confidence intervals did include the mean. Now you might be wondering, is there a correlation between the sample size and our success rate? And no, there's not. It's just I'm kind of getting lucky with the randomly selected samples that I'm taking. So again, I'm going to keep running this experiment, and you will see that after a handful of experiments, I'm up to about 1,200. I'm going to go up to 2,000 experiments. That's a lot, but it's easy to do when you have a little button. And we're about 96%. Yeah, it ends up averaging out over a long period of time that, yes, our success rate of our confidence interval will include our population mean about 95% of the time. But you have to realize that that means that 5% of the time, your confidence interval does not include the population mean.
Now, I'm sure you remember that I talked about very common confidence intervals. And I said 80, 90, 95, 98, 99. These are very common confidence levels that we use in statistics. Well, we also need to know the corresponding z-scores that go along with these confidence levels. Now, there are ways of figuring it out on the TI-84, but pretty much, if you kind of keep this little chart with you, your calculations will go a lot faster. If I wanted to find a confidence interval using the TI-84, first thing I have to do is actually calculate alpha. Alpha is 1 minus my confidence level. Now, confidence level is in decimal format. And then I'm going to use the inverse norm function. The inverse norm function needs 3 things: area, your population mean, and your population standard deviation. For the area, we are going to use 1 minus alpha divided by 2. Mu will be 0, and your sigma will be 1. Once I plug that into the calculator, it will spit out the z-score that corresponds with that. So let's say, for example, my confidence level is 95%, so I'm going to use 0.95. My alpha is going to be 1 minus 0.95. That's 0.05. So to figure it out in the TI-84, I'm going to plug in inverse norm, 1 minus my 0.05 divided by 2. For mu, I'll use 0, and for sigma, I'll use 1. And I get 1.96. Now, looking up at the table, it's 1.96. I say keep this little table with you. One less calculation that you're actually going to have to do to figure out the corresponding z-score that goes along with the confidence level. Like I said, unless it's some weird confidence level like 97 or 74, which I don't know we would ever go down to 74% confidence, these are pretty much the 5 that we're going to use over and over and over again. Let's focus on how to construct intervals. Now, there are some things that we need to understand. So the confidence interval will have this form. It's going to be our point estimate minus this margin of error, comma, our point estimate plus this margin of error. So it's going to be, our lower end is going to be minus this margin of error, and our high end is going to be plus this margin of error. In symbols, our point estimate for a population mean is going to be our sample mean, x bar. So x bar minus EBM, which stands for error-bound population mean, so just EBM. I've also seen this as used just in E. I'm going to stick with EBM because that's what our book does. So I'm going to stick with EBM, although I prefer just an E. It's less clunky. So our x bar minus our EBM, comma, x bar plus our EBM. Now, what our EBM is, this error will depend on our confidence level. Remember, the higher the confidence, this error is going to be larger. The smaller the confidence, the smaller the error. Now, there's another probability called alpha, and that's the Greek letter A. It looks like the normal A, but it is a Greek letter A. It's related to the confidence interval. Mathematically, it's alpha plus this confidence level will equal 1. So here's what this all means graphically. The shaded region is our confidence interval. We're using our point estimate of x bar, and we're going down a bit and up a bit. And we're hoping that we're in some confident level that our actual population mean lies between somewhere in this shaded region. Now, these tail areas that are not shaded, that's where our alpha lives. And because our alpha is a tail to the left and a tail to the right, that's why we divide alpha in half. So our confidence level is 1 minus our alpha. So if our confidence level was 95% or 0.95, our alpha would be 0.05. And those little tails would represent 0.025 of the information. So about 2.5% of our information lies within each of the tails. So we're going to be dealing with 2 tails all the time, and we're looking for the middle portion, which is our confidence interval. So there are 5 steps. The first step, we need to calculate the sample mean if we're not given that. If we're given it, cool. If we're not, we're going to have to calculate it. Now, we already know our standard deviation of our population. That will be a given. for at least this section, 8.1, it's going to be given to us. Then we're going to find the correlating z-score that corresponds to our confidence level. Most of the time, it's going to be one of those common confidence levels, and therefore just use your chart to say what the z-score is. If not, I'll show you a way of calculating it, but it's easier just to use the chart. Third step, we're going to calculate our margin of error, our EBM. Fourth step, we're going to construct our actual confidence interval. We're going to do the math to say x bar minus our EBM, x bar plus our EBM. And then 5, we're going to write a sentence to interpret what all this data means. So we've calculated some stuff, but the most important part is figuring out what this means. All right, so here's how we actually calculate the margin of error, the EBM. We're going to take our z-score that corresponds to our alpha divided by 2 and multiply that by our standard deviation divided by the square root of n. So let's say we have a confidence level of 95%. That would go along with a z-score of 1.96. Again, it's from that table. I've kind of memorized the most popular ones. So I would use 1.96. My sigma, let's say, is 2. My n is 10, so 2 over square root of 10. And you multiply that through, and you would get the error of margin. Now, when we're talking about how do we clearly state what we mean, how do we interpret it, generally it's going to be the same sentence over and over and over again. For example, we estimate within 95% confidence that the true population mean, and then we want to specifically say something about the problem, like the number of iTunes songs that are downloaded every month is between our values. And then we can say downloads if it was regarding downloads. But that's pretty much the generic statement that we can use. We estimate with some confidence that our true population mean regarding the problem is between these two values, which is going to be our low confidence value and our high confidence value. Let's run through an extremely simple example. Suppose we have a collection of data from a sample. We know the sample mean, but we do not know the mean for the entire population. I'm going to give you the sample mean. The sample mean is 7. I'm even going to give you the margin of error is based on a 95% confidence level, and I'm going to say this margin of error is 2.5. X bar is 7. EBM 2.5. And therefore our confidence interval is going to be 7 minus this 2.5, comma 7 plus 2.5. But you don't leave it like that. You actually do the calculation. So our confidence interval is 4.5, comma 9.5. That's our interval. But we also have to interpret it. We estimate with a 95% confidence that the true value of the population mean is between 4.5 and 9.5. The simple example was fun while it lasted, but let's get to a more appropriate example of what you're going to be facing. Suppose scores on exam and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. A random sample of 36 scores is taken and gives a sample mean of 68. Find a confidence interval estimate for the population on the exam score. Now we want to find explicitly a 90% confidence interval for the true population mean of the statistics exam scores. Here's what we're going to need. To find our error, we're going to have to find the correlating z-score. We're going to have to figure out what is our standard deviation, which is usually given to you, and we're going to have to figure out what our n is. So the first thing we want to do is pull out the information from the problem. X bar is the sample mean, and that sample mean is 68. Our formula we need to find our error bound is our z alpha over 2 times sigma over the square root of n. Now we're dealing with a 90% confidence, and therefore that correlates with a 1.645. Go back to the table and take a peek. 90% confidence is a 1.645. Our sigma, that's in the problem. And it says our population standard deviation of 3 points. So our sigma is 3. Our n is the number of scores that we took. A random sample of 36 scores is taken. So n is 36. And our confidence is 0.90. Throwing in our z, our sigma, and our n into our calculation, we get 1.645 times 3 divided by the square root of 36. In other words, 0.8225. Now this is our error. You can think of our error as a buffer. Now to calculate our actual interval, we're going to take our x bar and we're going to subtract this error. And then we're going to take our x bar and add this error. So 68 minus 0.8225, we get 67.1775. Taking our 68 and adding the 0.8225, we get 68.8225. So our 90% confidence interval is 67.1775 to 68.8225. Again, last step, always interpret. Interpret our meaning. It's not good enough just to have the interval. We estimate with a 90% confidence that the true population mean exam score for all statistics students is somewhere between 68.18 and 68.82. I just rounded to 2 decimal places. So it was those 5 steps. It doesn't look like too much. I think the trickiest, I wouldn't say there's any trickiness to it. You just have to remember whatever the confidence is to change it over to a z-score that correlates with your confidence. All right, let's go through a full walkthrough of a problem. The specific absorption rate, SAR, for a cell phone measures the amount of radio frequency RF energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the FCC, the Federal Communications Commission, for the sale in the United States, the SAR level for a cell phone must be no more than 1.6 watts per kilogram. The table shows the highest SAR levels for a random selection of cell phone models as measured by the FCC. We want to find a 98% confidence level for the true population mean of the specific absorption rate, SARs, for cell phones. We are going to assume that the population standard deviation, sigma, is 0.337. So at least we're given sigma, but we are not given our x bar. We're not given our sample mean. That means we have to calculate it ourselves. First step, we have got to get some information. We're going to have to calculate our x bar. We're going to have to figure out what our sigma, our n, and our confidence level is. So adding all of our data up, and I just used Excel. I threw it into Excel. I made Excel add it all up. I got 30.712, and then divided by the n of 30, I get our average of 1.024. Our sigma is given to us as 0.337. Our n was 30 values, and our confidence level is 0.98. Our second step is we need to find the z-score that corresponds to this confidence level. The good news is that 98% is one of those common confidence levels. So I can go look it up on my table and say that the z that corresponds with 98 is 2.33. Now you might be wondering, why is it z with a 0.01 as its little subscript? The z that we use correlates with alpha over 2. Our alpha is 0.02. 0.02 divided by 2 is 0.01. But an important part is our z that corresponds to 98% confidence is 2.33. Third step, we need to calculate our margin of error, our EBM. We're going to take that z, we're going to multiply it by the standard deviation over our square root of n. So we get 2.33 times 0.337, all divided by square root of 30. And that calculates as 0.1434. So our error is 0.1434. Now that we have our error and we know what our x bar is, we can construct our confidence interval. So step 4, we're going to construct our confidence interval. Take our x bar of 1.024 and subtract our EBM. So minus 0.1434 and we get 0.8806. We take our average and we add our error to it and we get 1.1674. So our confidence interval looks like a point because it's in parentheses with a comma. So parentheses 0.8806, comma, 1.1674, end parenthesis. That's the actual interval. But step 5 is we have to write a sentence that interprets this information. So you can always use the same language over and over again, just fill in the gaps. We estimate with a 98% confidence that the true SAR mean for the population of cell phones in the United States is between 0.8806 and 1.1674 watts per kilogram. Using the TI-84 Plus to build confidence intervals is pretty straightforward. The hardest part is going to be figuring out what data we need. To be able to plug it into the TI-84 Plus, we need the sample mean, X bar, we need our standard deviation, and we need to know what confidence level we'll want to build the interval with. Clear this out. I'm going to go right back to my home screen by going second quit. And then I'm going to click on stat. But this time we're going to run over to tests. And there's a long list of tests here. We want the z interval. Since we're dealing with population, we want the z interval. So I'm going to hit 7. And if I had some data where it was in the list, I would keep it on data. My list would be 1. If I did have some frequency in another list, I could use L2 for frequency and change my confidence interval. But in this example, I have the sample mean already, and I have the population standard deviation sigma. So I'm going to go over and use stats. So if my data is in a list, I would use data. If I don't, I'm going to use stats. My sigma is 2.2, my standard deviation. My average is 8.2. Oh, and I have to know how many I have. What's my N, which is 200 for this problem. And I actually want to build my confidence at 90%, so 0.90. And that's it. Those are the 4 information points I need to put in. The calculator will do the rest. And calculate. And there's my interval. So for this problem, my low point is 7.9441 and my high value is 8.4559. That's it. That's how you do a confidence interval when you have a single population mean. Now, if I did want to build a list, so I'm going to go ahead and clear my lists out. So I'm going to go to Stat, Clear Lists, and I'm going to clear my L1. So second L1. And now that my list is cleared, I'm going to go back and I'm going to edit my list. And this time I'm just going to put in some value. I don't want to be in L2. I honestly don't care about the values there. I'm going to say my values are 2.5, 2.3, 3.5. I'm just making up some data so you can see when I have a list how I would use a list. Now I do have to keep track of my n, 2.41 and 3.95. So I have 1, 2, 3, 4, 5, 6, 7. Let's put in a few more. 5.1. We'll put in a smaller one, 1.96. And I need one more just to make 10. Why not? Okay, so there's my list 1. I'm going to go back to stats. I'm going to go back to my tests, my Z interval, but this time I'm going to change it to data. Let's say my standard deviation is 0.59. My X average, I need to change it over to data. That's why it's asking me for all of this. I want it to be in data. So I'm going to hit enter. And my sigma, my list 1, my frequency is 1. And this time, let's say I want a confidence interval of 95% interval. And I calculate it. And therefore, my interval is 2.7433. So it grabbed the X bar from the actual calculation of my sample and also my standard deviation from my sample. So it grabbed that plus my N. So if I use a list, I'm going to use data. If I'm actually have my standard deviation and my sample mean, then I'm going to use stat. And that's it for this lesson. Until next time, be seeing you. Sometimes we have to work backwards. Now there's two parts of the interval. We have our mean and we have our error. And by doing a small calculation, we can get our interval, both our upper value and our lower value. What if we're not given one of those? What if we're not given the error, but we have the sample mean? Well, how we can find the error is from the upper value, we just subtract the mean. Or we can take the upper value and subtract the lower value and then divide in half, divide by 2. So that's if we are looking for the error and we are given the mean. If we need to find the mean, but we are given the error, then we're going to just subtract the error out of the upper value, and that will give us the mean. Or take the average of the upper and lower endpoints of our confidence interval, and that will give us our mean. So let's take a peek at an example. Let's calculate the error bound. We have this example. Suppose we know our confidence interval is 67.8, 67.82, and we want to find the error bound. We might know that the sample mean is 68. So let's try that first. Let's find our error given we already know our mean. Well, that means X minus our error will give us our lower bound, and X plus our error will give us our upper bound. So we can choose to use either one of those. That's just an algebra problem at that point. I'm going to take my upper bound. So 68 plus my error will give me 68.82. Solving it algebraically, subtracting 68 from both sides, I know my error is 0.82. That's if my mean is known. If my mean is not known, well, then I'm just going to take my high bound minus my low bound, and I'm going to divide by 2. So I'm looking for the difference between those values, and I'm going to divide it in 2. So 68.82 minus 67.18 divided by 2 is 0.82. So if I don't know the sample mean, that's okay. I can still calculate my error. Now let's calculate the sample mean where the error is known. This case, I know that my error is -0.82. Knowing where it came from, so X minus our EBM is our low value. X bar plus our EBM is our high value. So this is an algebra problem. I don't know the mean, but I know the EBM. So X bar minus 0.82 equals our low. X bar plus our 0.82 equals our high. So again, I'm just going to take that high value. So x bar plus 0.82 equals 68.82. Subtract the 0.82 from both sides, and I get my mean must be 68. That's when we know our error. If we don't know our error, that's okay. Our x bar will equal our high value plus our low value, all divided by 2. Now I want to restate that because our error, what we did when we were looking for our error, we subtracted the two values. When we're looking for our mean, we add the two values and divide by 2. So 67.18 plus 68.82 divided in 2 is 68. Many times we actually want a specific margin of error, and that margin of error is based on several things. So our error calculation is our z times our sigma over the square root of n. So the number of people that we ask is going to be a component of that calculation. So if we want to know how many people we do need to ask to have a certain margin of error and to have a certain confidence, we can solve our error equation for n. So we get n equals z squared times sigma squared all over our error squared. That's just algebra, solving for that variable. Let's take an example. The population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of Foothill College students, how many randomly selected Foothill College students must be surveyed? All right, we know sigma is 15. We also know we want to be 95% confident, so our confidence level is 0.95. Our error, we want to be within 2 years of the true population mean age, and therefore our EBM is 2. The corresponding Z that goes along with 95% confidence is 1.96. Now that we have our sigma, and we have our EBM, and we have our Z, we can throw it into the calculation and figure out how many people do we have to survey. N will equal 1.96 squared times 15 squared, all divided by 2 squared. We get 216.09. Now here's the thing. People do not come in 0.09 section. Therefore, when we're talking about N, we have to talk about whole people, and therefore we will always round up to the nearest integer. So 216.09, we'll need to ask 217 people must be surveyed. I want to take a step away from calculating confidence intervals to take a look at the notation of confidence intervals. We've been working with one type of notation, which is the open interval notation. So this should look very familiar to you. I've put both of the versions up on the screen where we're using EBM as well as just the letter E. And I'm doing that because you will see EBM notated in your book, but in your homework you will see just the letter E. So don't get confused. The E is exactly the same thing as EBM. It's just a shortened way of writing that. And so we would have our two values, our low value of our confidence interval and our high value of our confidence interval, and that is in a set of parentheses separated by a comma. I want to take a step away from calculating confidence intervals to take a look at the notation of confidence intervals. We've been working with one type of notation, which is the open interval notation. So this should look very familiar to you. I've put both of the versions up on the screen where we're using EBM as well as just the letter E. And I'm doing that because you will see EBM notated in your book, but in your homework you will see just the letter E. So don't get confused. The E is exactly the same thing as EBM. It's just a shortened way of writing that. And so we would have our two values, our low value of our confidence interval and our high value of our confidence interval, and that is in a set of parentheses separated by a comma. We also have two other ways of writing a confidence interval. One is called the Inequality notation, and the other is the point estimate margin of error notation. Both of these notations give you a lot of information. They're not calculated differently. I want to stress that. They are not calculated differently. It's just displaying the information in a different manner. For the Inequality notation, we take our low value is less than or equal to our mean, less than or equal to our high value of our confidence interval. To me, this is very clearly defining what we are actually looking for. We're looking for our population mean, and we're estimating it that it is between these two values. Our point estimate margin of error notation literally is that. We use our point estimate, which we've been using X bar, so that's why I have that there. And we use the symbol plus minus, our EBM. So we're not doing the math. We are literally displaying what our sample average is and what our error is, and we're leaving it as a plus minus situation. So you will see confidence intervals written in all three of these manners: open interval, the Inequality, and the point estimate margin of error. Be careful when you're running through your homework that you put your interval in the correct notation that the question is asking for.
You've reached the end of this lesson.